This may be a trip down memory lane to probability and statistics. We're talking correlations. It's just a modest overview, so don't panic. So what is a correlation? Very simply, a correlation is a relationship between variables. Yes, of course, you've all heard correlation does not equal causation, but it doesn't mean that they're not related to each other, and sometimes, in fact, those correlations are causal in nature. Example is sugar and sweetness. Often when something is sweeter, we know there's more sugar, right? It is sweeter and there's more sugar. As we add more sugar, the thing will be sweeter, right? Those things correlate to each other. Heat and dehydration. As the temperature goes up, so do cases of dehydration. As temperatures go down, fewer cases of dehydration. But not all correlations necessarily things move in the same direction. They may move in opposite directions. So the weight of a car and gas mileage. As a car gets heavier, the gas mileage goes down, right? So weight goes up, gas mileage goes down, weight of the car goes down, gas mileage goes up. Not always, but often we see there's a correlation there. It's not every time, but generally speaking, it's a correlation we find. Also, age and eyesight. No one at 15 is told, your vision's not very good, but maybe in 20 years it'll be better. I mean, okay, there's probably one person who gets told that, right? But the point is, we expect as you get older, right, your age goes up, eyesight we expect to go down, really past the age of 4 or 5, right? That's what we're going to see happen, right? As you get older, right, age goes up, eyesight goes down. So relationships can be such where things move in similar directions or they move in opposite directions, but those are all correlations. So in talking about correlations, I said they can move in different directions or they can move together. Let's talk about what I'm referring to. Some of those are positive relationships. So a positive correlation is when variables move in the same direction. As an example, as we consume more calories, we gain more weight, right? More calories, more weight, right? As I eat more, my pants get tighter, right? There's a correlation there. As I eat less, my pants get less tight, right? So that's a positive correlation because calories go up, weight goes up, calories go down, weight goes down. Hours studying in course grade. Generally speaking, within a given course, the hours a person spends studying, the higher their course grade, the fewer hours they spend studying, the lower the course grade, right? And so that positive relationship doesn't mean numbers always move up. It means that those variables move together, right? Calories up, weight up. Likewise, calories down, weight goes down. So that it's positive because it means whatever direction they're moving, they move together. So positive is like a friendship, right? You have a positive relationship with somebody, you're friends with them. If they go up, you want to go up with them. If they go down, you want to go down with them, right? It's a positive relationship. So if we have a positive correlation or a positive relationship, we can also have a negative relationship or a negative correlation. And this is when variables move in opposite directions. It doesn't mean variables move down, it means they move away from each other. So if you have a negative relationship with somebody, if they go up, you want to go down. If they're going down, then you want to go up, right? You don't want to be around them. So exercise and blood pressure. As people exercise more, right, their exercise goes up, blood pressure usually goes down. As people miss classes, right, they have more misses, the number of misses goes up, course grade goes down. Number of misses goes down, course grade goes up, right? So an up is paired with a down is paired with an up, right? That's a negative correlation because they're moving in opposite directions. So it's not they're both moving down, it's that they move in opposite directions. Because if two things move down together, that's actually a positive correlation. So what do the numbers mean? When we look at a correlation, as you're going to be looking at your paper, what do the numbers mean? So correlations, the type you'll be doing, are represented by the letter R. Just a little lowercase r. I think technically a Pearson's product coefficient R, but why don't we just call it R as friends? Let's just call it R, okay? And so it describes the effect size in relation to the numbers. So how strong is the relationship between numbers? And I say in relation to the number 1, because no correlation will ever be greater than the number 1, because 1 is the same as 100%. And so the only thing you can ever correlate with 100% is yourself, right? So no number ever 100% correlates really with any other number unless you somehow replicated a data set. I mean, this doesn't happen. The only person who's completely like you is you, right? Not even identical twins are completely alike. So, so everything is less than 1, but the closer to 1, right? The closer to 1 something is, the more like it is, right? And so 0.9 is closer to 1 than a 0.3. So we have this thing called effect size, and there's the scale for you all at once, right? A small effect size is when the R equals like 0.1 or somewhere around there, right? These variables are loosely related. They are related to each other. They do move. They do move. If one goes up, the other one goes up, or if one goes up, the other one goes down, and that happens consistently. But it's pretty loose. Like their relationship to each other, if one goes up a bunch, the other one probably goes up a little. I mean, like it's a very loose relationship. It's not very strong. So a medium effect size, um, it's not necessarily 0.3, it might be 0.25. I mean, getting sort of, as you closer you get to 0.3 is a medium effect size. These variables are more interesting. The small effect size, those variables, we don't care a whole lot about that. We are interested in variables that have a medium effect size, right? There's a sort of a decent relationship. We know that one variable has a fairly decent impact on the other one. It's not huge, but it's respectable. And so if we can play around with one variable, we can change the outcome of the other variable. And then a large effect size, it doesn't have to be right at 0.5, maybe it's a 0.45. As you get closer to 0.5 or 0.50, this is a large effect size, which means the variables have a pretty strong relationship with each other. Some variables will have a greater than 0.5 a lot, or I mean, significantly greater than 0.5. I should probably use the word significance with statistics, but that's a whole other story. But sometimes you'll see an effect size that maybe it's a 0.75, a 0.8, a 0.9. Those are a very large effect size, and typically those are the sort of things we don't even go looking for the correlation because it's a well duh sort of relationship. So if you have something that correlates at 0.52, you go, well, 0.52, that's not a very big number in relationship to 1. Actually, in terms of a correlation, that's very large, or that's large, I should say. That is large. That's really pretty good. So that's what we're looking at with these numbers. It's just a general sense of how strong is the relationship of one number to the other, whether those numbers are moving together or away from each other. It's about consistently what is their relationship to each other.